Can everybody hear me?
Yeah.
Yes?
It's not can now.
First. Stand right in front. Okay. So, to introduce what we are about in tonight's meeting, our featured speaker is John Valley, who I'll introduce in a moment. He's going to be speaking on star and planet formation behind the Orion Nebula. Then we're going to have, after his presentation, observing reports, and Fred Goodman is going to talk about the eclipse telescope inventory briefly. We'll have a break, and we want to, regardless of where we are at that point, we want to be back at 7:50 to start the second half of the meeting. We would hope for about a 15-minute break as usual. Then it's Vince Felt with What's Up, Outreach Reports from Dave Warner, Scott Donnell, Treasurer Reports, and our committee reports. And we hope to adjourn at 8:30. So I would like to announce who our executive committee is. Matt Russell, our president. Everybody wish him happy birthday.
Happy birthday.
Happy birthday, Matt. Yay.
I read in the newspaper that he was born.
He is viewing. He's viewing.
He's online live and viewing. I read in the newspaper he was born 2 days after Apollo 11 landed. That's how I read it. So my name is Doug Cook. I'm Vice President in for Matt. Our treasurer is Scott Donnell. Secretary is Vicki Kitzman, back there. Member at large, Tom Mulligan. Tom, are you here?
I'm here.
There. Associate Director, George White. George is our trustees are, there's a book out in the back, and again, Scott Donnell. And our webmaster is not here, that's Stephen Lehman. Wish him well. I know we have some new visitors tonight, and that is one or two of you. And at this time, we'd like you, as a new visitor, to introduce yourself, or new members, introduce yourself and tell us how you heard about us and what are your interests in being here and how Colorado Springs Astronautical Society. So new members.
So I'm blocking the screen.
Stand up and
We'll try.
in front.
Or you can probably do a little bit of both.
My name is Terrence. My first time listening here, of course, but my interest is basically just want to learn how to telescope properly. It's something to help my kids out so I can start letting them watch the stars with me at night. It's pretty much right here. My uncle Fred Goodman, he introduced me to this place and said, come on down and take a look at things. So, well.
And I think you filled out the visitor's card. We have this card on the front table with visitor. Please fill that out so we can reach out to you later.
I'm Andrew Booth. I work with I've been in astronomy since I was in high school, 20 years ago. I'm sitting on a brand new telescope in my room that I purchased back here in June, and I'd like to get in on some watch parties. Let's see what you guys are all about. Yeah, absolute first time. So,
Have you seen our calendar on CSASTRO? Our calendar has all of our outreach serving events.
I just got a watch party university party just last weekend. So yeah, that's some of my biggest interests here. But yeah, that's the cobwebs off my astronomy brain. Get back in action.
Welcome.
My name is Aaron Lorenzo, an X-ray tech. I'm actually a volunteer here at the Foundation.
Right.
So y'all were doing a meeting that day, and I saw y'all coming through. I didn't have a chance to stay that night, but I was interested. My primary thing, I'm just kind of getting back into space because for 27 years I kind of forgot about space, and then finally I got reintroduced to McDonald's or down in Texas. And I was kind of picking up right about it all. just getting back into it.
Great. Go ahead.
My name is Angelica, but I love cars. And
We're glad to have you at the meeting, and by all means, come to a star point. Yes, go ahead.
that's it.
We think you're well immersed if you come to one of our star points. Sure, welcome.
Mike Willison, came down from Denver, the first time I've been here. Been imaging comets for about 25 years. Recently sold my home, so I've been looking for other areas to move to or places to come image. So I came down to see what goes on here.
Welcome.
I'm Larry Sager, this is my wife Carol, and just became members of the society this time, about 2 weeks ago. Last fire I had from the society here was in 2003. It's been a while. But just getting back in it and starting to enjoy everything. Missed so many years.
Did you get signed up for a name tag?
No, I didn't.
Okay, you can, when you get a chance, you can see Vicki back there, put your name down, we'll get you the official name tag. And any other new members that have joined and don't have a name tag, see Vicki, our secretary back there. Or, everybody knows, new visitors.
My name's Nate, so I worked in satellite tracking kind of contract with the Air Force. So I was curious to kind of visit here and kind of get more of a stargazing and kind of scientific viewpoint, opposed to more like a software kind of role. So I know you guys do some satellite tracking as well, or kind of, you have kind of satellite tracking, software products, something like that. So kind of just interested in talking to people who have some experience with that as well.
Maybe at the break, anybody who's doing that can find you.
Thank you.
All right, well. Okay, anybody else just visiting? Heard that. And I will move on to an announcement about Dave Warner. Many of you have probably heard that he's not been officially recognized. That Dave earned the United We Serve Award. It recognizes government employees who demonstrated sustained excellence in volunteer service leading to significant positive outcomes for their communities. These individuals must have demonstrated exceptional leadership skills in recruiting, inspiring, and coordinating groups of volunteers, devoting substantial time and effort to the advancement of volunteerism. And I think we all know that Dave is the leader of our office, which is tireless in what he's done to serve his club and his community and outreach. He's been recognized for that. Congratulations. And now, Dave has his own announcement.
I will say before that when I got that award and that I let everybody know that to where I got the award and my organization, I work for Air Force Base Command, put me in for that award. I stand on the shoulders of giants, meaning that in order to do outreach, in order to do the things that we do in doing space and astronomy education for our Colorado Springs area public, takes all of you. It takes a team. And so I accepted that award on behalf of the Colorado Springs Astronomical Society and all of the members that are there to support everything that we do for our community. So my announcement, this is kind of cool. Nobody knows this except Matt, who wasn't going to be here for this meeting, but I was looking on the Astronomical League website, as I regularly do, and I try to post on our CSASTRO news forums on our webpage the latest stuff that's going on. And I saw that there's some new outreach awards. One of them I'm working on, trying to get that Apollo 11, get the Apollo observing sites, and so I can get that observing award. But there's another one that was on there, and I thought that there was a perfect opportunity for another award to be gained and won. So Bruce Bookout, can you come up here, please?
Yes, sir.
Man, fired. Okay. What did I do? Did I do something?
If any, you absolutely did. If anybody that's been in the club for any amount of time knows, Bruce Bookout has been a phenomenal leader in doing outreach. That it doesn't matter where you're at, whether you're at RMSS, September Sky Star Scare, at a meeting, or you're coming out to one of our outreach events. If you want to know and learn a little more about what's going on in astronomy and how to use your telescope and how to advance your knowledge, one of the guys to go to is Bruce Bookout here. Well, the new outreach award that they just came out with is the Mentor Award. So I put you in for the Mentor Award, Bruce. And
mental,
yeah. So Bruce Bookout.
My hearing's a little bad. Mental.
So Bruce Bookout is one of the very first recipients of the Mentor Award from the Astronomical League.
I don't know what to say. This was unexpected. So this should be picked up by every member in here. We all mentor each other. The mentoring I've gotten from so many other members is phenomenal. I've learned so much out of you folks, and I turn that around and put that back into the teaching that I do. And especially those folks who also need to be recognized on this at RMSS, when we have our students from Pikes Peak Community College come in and do stuff, that's fantastic. That's great mentoring. Bob, you come to mind every time for that. So, but thank you. I appreciate that.
Announcements. One is that Rocky Mountain Star Stare was a huge success this year. Those of you who turned out, thanks for coming, and we set attendance records, revenue records. We're going to hear more about that. We have our committee reports. And the last thing I want to do is thank the Space Foundation for hosting us. They are wonderful hosts, and Tabitha especially helped us set up this room. We won't have to tear it down afterwards. Let's just release the area if there's any trash around. And the final thing is that we had the Apollo 11 50th anniversary event here, and Colorado Springs Astronomical Society. We had the solar telescopes out. Dave was there and outreaching to kids. I had meteorites. And we also had several of our members interviewed. It was here at the front page of the Gazette. If anybody is interested, there was an interview with Scott Donnell for his book out, and with Matt Russell on their remembrances of the Apollo 11 anniversary. So I'll leave this over here on the table if you want to look at it during the break. So now I would like to introduce our speaker for the evening, Dr. John Valley. He's from the Center for Astrophysics and Space Astronomy at CU Boulder. This talk is on star and planet formation in Orion. John did his undergraduate studies at Berkeley and obtained his PhD at the University of Massachusetts in millimeter wave radio astronomy in 1980. Joined AT&T Bell Laboratories for 11 years And he actually worked with the group that discovered the cosmic microwave background. And there he studied interstellar molecular clouds, the outflows and jets produced by forming stars. And he participated in several expeditions to the South Pole and Antarctica to set up the first permanent astronomical observatory there. He's been a professor in astrophysics at CU Boulder since 1991. He uses many of the world's major observatories, such as Hubble and the Atacama Large Millimeter Array, or ALMA. He just told me as he walked in, he's pleased to learn that he just got some important observing time on the ALMA array. His research includes formation of stars and planetary systems and studies the extreme conditions around the Milky Way's 4 million solar mass supermassive black hole. He participated in observations of recent neutron star merger. And what he's going to speak about tonight is looking at stellar collisions and dense clusters, such as the event that occurred behind the Orion Nebula about 550 years ago. He's rekindled his interest in cosmology and is exploring the hypothesis that black holes produce universes. That's deep. Johnson Evans here has a moment of pride and courage where he operates a small observatory. I'd like to introduce John Bell.
Thank you. So, a quick question: why don't we brighten the projector or shut all the lights off? My talk is going to be very visual. I hope you can see the screen as well as possible. Well, we'll do as much as we can.
I'll hold these other lines down.
Yeah.
I'll work on that.
Okay. Perfect.
Okay.
So why star time formation? Well, first of all, a general statement. The formation of stars determines how ordinary matter in this universe evolves. In the Big Bang, it uses nothing but hydrogen and helium, and a tiny bit of a few of the lighter heavy elements. Nothing else. No carbon, nitrogen, oxygen, etc. All that stuff comes from stars. And how hydrogen and helium is converted into heavier elements is determined in first order by the mix of massive stars versus low mass stars. And that mix is a product of star formation. Now, stars not only make the elements, but they're also the environment. Star formation is the environment where planets are formed. So the process of star formation is exactly where you have to go to understand where planetary systems are born. And so one of the closest environments where we can study this process of how stars form is Orion. Now, the subject of star formation is actually very recent because we live in astronomy in an absolutely revolutionary era. You and I are part of the first generation in the history of this planet with access to the entire spectrum. Up until about the 1930s, all of astronomy was visual wavelength astronomy. Starting at about 1929, we had started piece by piece gaining access to other parts of the spectrum. First, radio waves. With the advent of rockets and satellites, we were able to get above Earth's atmosphere for the first time in the 60s, and that opened up the universe to exploration with telescopes that operate from gamma rays, X-rays, infrared, radio waves. And for star formation, we have to go to these other wavelengths because stars form in dense lighter clouds, which are completely opaque, mostly opaque at visual wavelengths. We have to go infrared and radio and X-ray wavelengths to see the process in action. And so that's why we live in an absolutely unique time. We are the first generation to explore the cosmos the way it actually is. Because we now, for the first time, have tools such as the Hubble Space Telescope. In a few years, we'll launch the James Webb Space Telescope. We just commissioned about 5 years ago the Atacama Large Millimeter Array, which I described to you as it's the Hubble Space Telescope on the ground. The images it delivers are 10 times sharper than Hubble at millimeter wavelengths. And you'll see a few examples of this. Right. First, introduction to Orion. This is Orion as you see it with the naked eye. There's Betelgeuse, Rigel, the three belt stars, the famous Orion Nebula in the middle. That image shows you about what you can see through a dark sky. So there's a record image. This is Orion's setting, and we're going to zoom into that region behind the Orion Nebula because that's one of the most interesting regions of star formation, and the nearest one where massive stars are forming. Now, if you take a much deeper exposure, here's Orion again, this is Betelgeuse, Rigel. Bells are almost lost because we're going down to about 11th or 12th magnitude here. Winter Milky Way is stretched across here. The Pleiades cluster is sitting up here. The object called the California Nebula is that region of red hydrogen. The Rosette Nebula, if you're familiar with that, sits right here. There again is Orion. And you notice that the entire constellation is surrounded by this arc, which was called okay, so what that help. That way, perfect. Okay, good. So there's this bubble up here, and there's this arc called Barnard's Loop. This is actually first seen on the early days of astronomical photography in the 1890s by E. Barnard. It took literally week-long exposures using Hubble telescope, basically a camera lens, 4-inch photographic plate. You get onto a guide star at sunset, would manually track that star across the sky until it keep on, close the shutter, and go to sleep. Next night, you would reacquire the same star, continued exposure for 1 week, went into the dark developed plate, found these luminous objects in Orion, which are much, much bigger than the Orion Nebula. Today, we can record this in 60 seconds with digital cameras. By the way, I'm going to retune your brains. Why we go to the infrared is the following slide. This is a visual, half a micron wavelength. We'll show you what the same scene looks like at 100 microns wavelength, 200 times the wavelength of visual light. This is registered. There you see Betelgeuse in the infrared, looks blue. And you see almost all the stars have disappeared because at 100 microns in the infrared, it's not a star-studded sky, it's a cloud-filled sky. The sky is filled with dense clouds, such as the one right behind the Orion Nebula, right there, and right next to the Porcelain Nebula right there. This is the environment from which stars are born today. Now, we'll talk about this region in a little bit more detail, but let me just get you a little more familiar with the stars in this region. This is back to the southern all-sky shot of all sky. 1 radian of the sky in winter. There's Orion again, the Orion Nebula. Now, pointing out these 2 stars, one's in Auriga, 8B Auriga. 8B and Blau in the 1950s, using photography, found that those stars are moving across the sky at a speed of about 150 kilometers per second to the north. And this star down here, called Mu Columbae, just off the edge of this picture, is moving south at 117 kilometers per second. In the late 90s, 1990s, the European satellite called Hipparcos measured their proper motions and distances accurately, and traced back the motion of this star right below the Orion Nebula, and this star right below the Orion Nebula, to another star called Ioga Auriga, which is the brightest star in the Sword region, just south of the Orion Nebula. It turns out 2.5 million years ago, 4 stars interacted, their mutual gravitation. Exchanged partners, there were 2 double stars. We think they exchanged partners and ejected 2 stars at 100 kilometers per second plus. That's 2.5 million years ago, with an error of about 50,000 years. I'm going to tell you today, so in the last few years, we realized that a similar phenomenon happened behind the Orion Nebula a mere 550 years ago. That's actually when the light signal would have gotten here. The event actually happened 1,300 years before then because of light travel time, right? Light travels at a finite speed, therefore telescopes are time machines. We look back in time and we look ever further into space. We see Orion today way it was 1,300 years ago. We see the galactic center the way it was 30,000 years ago. We see the Andromeda galaxy the way it was 2 million years ago. The further you look into space, the deeper you look back into time. So the Orion event happened in the year AD 175, when guess who was Emperor of Rome? No? Marcus Aurelius. Signal got here in 1475 AD. It's too bad that some monk in Europe didn't have an infrared telescope looking around. He would have seen one hell of a bright flash of light that would have lasted for probably a decade. Right, so this is Orion. We'll zoom in a little bit closer. If I subtract all the stars, this is an H-alpha image, very deep, covering 30 degrees of sky. Here's Barnard's Loop, the Orion Nebula, the Porcelain region, Milky Way. You see this is chock full of glowing hydrogen. what we call a super bubble. Orion has an inflated bubble that's 30 degrees across over the course of the last 4 or 5 million years. What's created that bubble? Supernovae. Orion's been forming stars for at least 10 million years. It's probably produced well over 20,000 stars as of today. Hundreds of those stars are massive. At least 2 or 3 dozen have already died, exploding as supernovae. In fact, just in the last few years, we found evidence that Barnard's Loop is merely the youngest supernova remnant in Orion. Supernova that blew up there about 300,000 years ago, created Barnard's Loop. Actual bubble walls made out here. And stars are still forming in these 2 regions. And already there's massive stars which we know will die in the next million years or so. So there'll be another 2 or 3 or 4 supernovae in Orion coming up in the next few million years. I'm going to zoom in a little bit. This, by the way, took from Breckenridge. It's about a 1-minute exposure for just a DSLR. Here's the Orion Nebula, Horsehead, Barnard's Loop. And now I'm going to retune your eyes again using the Planck satellite the Europeans launched 2 years ago, 2009, to show you what this scene looks like as what we call sub-millimeter wavelengths. Wavelengths about 0.3 millimeters to about 1 millimeter. A little bit long, about 1 centimeter as well. This is Orion, as seen by the Planck satellite. By the way, I've converted the wavelengths to frequency units, so this is 500 gigahertz in the green and 30 gigahertz in the red. And what you're seeing is Barnard's Loop, and you're seeing those molecular clouds right behind the Orion Nebula in green, up here and up here. We'll zoom into that in a little bit more detail. One question is, how much stuff is there in these clouds? I found the Planck data, which is basically tracing interstellar dust that absorbs sunlight and starlight, absorbs that energy, the dust grains warm up to about 20 degrees below absolute zero, and they radiate at these sub-millimeter frequencies of, say, 500 gigahertz, okay? So we can measure mass in these clouds. Answer is that this cloud contains about 50,000 times the mass of our sun. And this cloud contains another 30 or 40,000 times the mass of our sun. In other words, there's a lot more stuff that can make stars in Orion today than a number of stars. So star formation is still very active in this region. But way back in the 1980s, when I was at Bell Labs, I wanted to see what this cloud looked like in an interstellar molecule. So I used the Crawford Hill antenna over a course of about 6 months to map Orion in a molecule called carbon monoxide, which you've heard about. It's a poisonous gas, but it's abundant in interstellar clouds. In fact, it's the 3rd most abundant species. Hydrogen, in its molecular form, is the most abundant species. Helium, left over from the Big Bang and somewhat made from stars, is the 2nd most abundant species. Next comes carbon monoxide. That's great because we map how clouds move in a line of sight by mapping the carbon monoxide. So here's the same scene as seen in carbon monoxide. And by the way, you ask, what are the colors now? The colors are Doppler shaped. Red is redshifted by a few miles per second. Green is in the middle of the typical velocity of Orion. And blue is blue shifted about 4 miles per second. That's what you see immediately. So behind the Orion Nebula, there's a gradient. There's a variation of velocity along the line of sight. Stuff here is moving away, stuff here is approaching compared to the stuff in the middle. The Orion Nebula sits right in here, as we'll see in a minute. I want to zoom into this region because there's a familiar object there. Some of you who have nice telescopes, called the Horsehead Nebula. I'll get there in a minute. So if you want to see where the young stars are, by the way, this shows you where the Orion Nebula is. This is an infrared view, now 22 microns of the wide satellite. That is the bubble created by the young stars in the Orion Nebula today. By the way, those stars are very young. I mentioned that stars have been forming for about 10 million years in Orion. Orion's massive stars are just emerging now. I think no more than 20 or 30,000 years ago when they started emerging from their parent clouds. So this is the youngest region of star formation. Along with those massive stars, Orion over the last million years or so has spawned about 2,000 young stars. And we've now observed hundreds of protoplanetary systems where young planets are thought to be forming around those stars today. By the way, we now know also because of European Gaia satellite, but the distances to various parts of the Orion are for the first time. So here is a three-dimensional view. Here's again this Orion A cloud, as we call it. Cloud next to the horse head. And this is distance in parsecs. Basically, 1 parsec is about 3 light years. So if you multiply these numbers by 3, you get the distance in light years. So this 410 is roughly about 1,200 light years away. The Orion Nebula is the head of this cloud. Here. And the tail, which is approaching us, is actually further away from us. So it looks like the whole cloud in 3D is doing something like this. Like the upper part is moving away compared to the bottom part. Okay, go back to this carbon monoxide map again. By the way, you might notice that this has 13 on it. This is the rare isotope of carbon. Most carbon has 6 protons and 6 neutrons. The atomic mass number is 12. Add an extra neutron in a rare species of carbon monoxide called 13 carbon monoxide. Use it to map clouds because in the common isotope of 12 carbon, the CO is so much carbon monoxide that you cannot see into the cloud. You only see the surface of the cloud. It's like the moon. You only see the surface, you can't look into it. Or the sun, you only see the surface, the photosphere, you can't see into it. You need a tracer, which is less abundant, which is optical, is transparent, translucent. 13 CO is translucent enough so you can see the interior of the cloud. Okay. So, zoom back out again. This is a really nice deep visual view of the entire constellation. Betelgeuse up there, laser here. Betelgeuse, Rigel, 3 belt stars. You now see the Vega-type young, luminous, moderately massive stars like Vega, by the hundreds clustered around the belt. You can see Orion Nebula as a bubble. You can see Barnard's Loop, which is this young 300,000-year-old supernova. You also see next to Rigel, this cloud which has been dubbed the Witchhead Nebula, which is blue because it's basically shining by reflected light from Rigel itself. Now, one interesting little tidbit, the Gaia satellite and Department before has told us that this star is far in front of Orion. This is only 200 parsecs away, whereas this part of the cloud is about 400 parsecs away. So Rigel is in the foreground, and Betelgeuse is also in the foreground. By the way, Betelgeuse, just like those 2 stars I showed earlier, are moving at 100 kilometers per second. Betelgeuse is also a runaway. It's moving at 20 kilometers per second on the left. It also was ejected by some process, similar to what I'll talk about in a few minutes in a line. Zooming in a little bit into this little box, we see now the Horsehead Nebula next to the 3 bright belt stars and that swarm of 8 spectral type stars on Vega. Down here, the so-called sword region has the Orion Nebula. Half a degree north is NGC 1977, another little bubble of ionized gas. There's an older cluster, about 5 million years old, up here called NGC 1981. And then just below it, the Orion Nebula, is this star, Iota Ori. That's the star that 2.5 million years ago was responsible for ejecting those 2 runaway stars, one located in the right of, and the other located south of Orion, the constellation of Columba. What's Columba? Anyone know the name of that constellation, what it stands for? 88 constellations. That's not one of your well-known constellations, believe me. By the way, here's a close-up of the Horsehead visual. You retune your eyes to carbon monoxide, now the common isotope, 12 carbon. Here's the molecular cloud. What is dark in this picture on the left glows in molecules of carbon monoxide. The colors again are dopplershapes. You can tell how the molecules are moving away from us or towards us with a precision that's of order of tens to 100 meters per second, independent of the distance. All right, we'll now zoom into the Orion Nebula itself. So this is a 1 square degree view centered on the Orion Nebula. There's the cavity you can see. Right next door to Orion is a smaller cavity called Messier 43. I'll just show you a close-up of that, and we'll This is a nice near-infrared view. You can see the dusty clouds, again, molecular clouds. Nice photo, which I'll point out in a minute here. And right in this little box is that faint little star. That's the first example of a protoplanetary disk I'm going to show you. That star, when you look at it with the Hubble Space Telescope, which is a part of the view of Hubble, took actually 2 sets of images of Hubble, separated by about 2 years. And what I'm doing is I'm blinking the first epoch with the second epoch. And you see there's a star, there's a disk, there's a companion star right next door, and there's a jet coming out. You've actually seen the motion of the plasma that's ejected from that star. And if you calculate the amount of motion and the units, convert that to physical units of the distance, you divide by the time interval, you get the speed. The answer is that that jet coming out of the star on both sides is going to be about 200 kilometers per second. We've learned that almost all stars accrete most of their material through accretion disks like this. The matter spirals onto the central star, magnetic fields get wrapped up, and the magnetic energy tends to launch high-velocity jets along the spin axis of the disk. Very common phenomenon. We'll show you some other examples in a few minutes. By the way, maybe you were almost commissioned. We went and looked at this same object with the Atacama Large Millimeter Array. So here's the H-alpha image with the Hubble Space Telescope. You see this companion star. You can see this disk in silhouette. You see a little bit of a hint of that central star. When we go to ALMA, we measure the dust emission in those protoplanetary disks. And what we learned is that both stars are surrounded by disks, as revealed by dust emission at 0.85 millimeters. And we also learned to measure these rate at which molecules in this disk are going around the central star. We use Kepler's laws to measure the stellar masses. What we found is that this star is 3 solar masses. This star is only 0.8. So actually, the dimmer star is the most massive star. It's only dim because it's so embedded in this planetary disk. Most of the starlight doesn't get out. It gets absorbed and reprocessed into infrared. I'll show you the kind of instrumentation we use to make maps of these molecular clouds. So back until 2015, there's an institute in California called the California Array for Millimeter Astronomy, and unfortunately it was decommissioned in 2015, just as we were learning to use it. This is a consequence of federal cutbacks by the National Science Foundation. They invested $80 million over the years to build this facility. To save $1.5 million that particular fiscal year, they closed the array. That was a disaster for our science, and foolish. Because as a consequence of this, they're literally turning over our ability to do millimeter astronomy to other nations. Right now, it's the Chinese, it's the Europeans. We are not competitive anymore in millimeter technology because we're not funding it. And that's, I think, devastating for our science. But we used this facility for 6 months before we shut down to map 2 square degrees of Orion with a resolution of 6 arc seconds. And I'll show you the results. So here's again Orion with the infrared, and registered are several slices of a data cube showing how the molecules of carbon monoxide move along line of sight. Again, the numbers up here are the weighted gases moving in tons per second, kilometers per second along line of sight. So 5 kilometers per second, 7, and 9 correspond to blue, green, and red. If you blink this image, you notice that this dust filament, M43, corresponds in this particular rendition to this red structure here, which is at 9 kilometers per second. If I switch to filter, here's another part of the data cube. 6, 8, and 10. This filament is almost gone. You see this bright bar, you see this edge, and notice that this edge, if you go back to the pictures, corresponds to this edge in the Orion Nebula. You're seeing the actual front, where the hot plasma, ionized by those massive stars born in Orion, are creating a cavity in the molecular cloud. And that's what the data cube looks like. This is the kind of data we're now working with, these interferometers. What does Hubble see here? Well, this is the Hubble Space Telescope view of the core of the nebula. So if I go back to this picture here, Zoom into this little box here. You see 3 stars, 1, 2, 3. These are called theta 2 Orionis A, B, and C. In the middle here is a trapezium. You can see easily with a small telescope. And if you zoom in, here's theta 2A, B, and C is just out of the picture. There's the 4 stars that you can easily see with a small telescope called a trapezium, along with hundreds of much dimmer stars, most of which were born within the last million years. If you zoom into the trapezium itself, there's a brighter star. This is a 40 solar mass star. This is about a 15 solar mass star. And in fact, every one of these stars is multiple. This guy is a triple. This guy is a triple. This guy's a quintuple. This guy's a double. Multiples are the norm amongst massive stars. You also see something somewhat funny. These stars don't look right. They have tails. And one of my colleagues who sadly passed away a few years ago, my father, coined the term way back in the 60s called partially ionized globules. PIGs. Can I honestly say, these have tails. They all point away from the most massive star in the region. What causes these tails? The evaporation of protoplanetary disks, where young planetary systems are in the process of formation. If you zoom in even closer to the Hubble Space Telescope, here's one of those partially ionized globules. You can see a faint disk in the shadow here, and a tail, almost like a comet tail. Here's another one, a comet tail. And this one, you can actually see the disk edge on. The blue glow turns out to be atomic oxygen edges of that disk. And here's a pure silhouette disk, where you can see the central star, not the star directly, but a little reflection they go out just above the star. And by the way, these are huge. This disk has a radius that's about 400 astronomical units. This is about 10 times bigger than our solar system. So these environments where planets form tend to be massive and big, much bigger than our solar system. 30 days. By the way, here's a close-up of that silhouette disk. Here's the optical image. You see it in silhouette. In the middle, this is the ALMA, Atacama Large Lunar Array, emission from dust. And it turns out that from the rotation, it's blue shift and red shift and the carbon monoxide, we inferred that the stellar mass is only 0.4 times the mass of the sun. This is going to be the red dwarf, not a sun-like star. As I mentioned, there are hundreds of planetary systems forming in the line. This is just a rose gallery from Massimo Roberto's survey a few years back in about 2010 timeframe. And you see these extended objects around almost all the stars in the line. You can see some of these things have a beautiful disk. We call this object, by the way, the beehive. You can see these rings. In fact, a colleague of mine next week is visiting me from Hawaii. We're about to write a paper on that object because we found that these rings are moving down toward the south. Something is pushing those rings down, so we're writing a paper about that. ALMA's also gotten into this game. Here's an ALMA image of some protoplanetary disks in the constellation Taurus. This one made a press release about 3 years ago. It's called HL Poweri, right behind the Hydraean star cluster. The resolution here is astonishing. The diameter of this disk is 1 arcsecond. ALMA's resolution was 0.02 arcseconds. That's a factor 3 sharper than the Hubble Space Telescope. Here's the young triple system that was just published recently by John Hilden. One star there, another star there. And what you're seeing is not the star itself, but dust heaving vicinity of those forming stars. And this looks somewhat reminiscent of a spiral galaxy. The dynamics of orbital motion being spiral arms with these protoplanetary disks. And on the left side, these gaps, some have hypothesized, may be produced by protoplanets. Protoplanets clear gaps when they get to about half the size of the planet Earth by gravitational forces. They clear out a region. And so we think there might be protoplanets embedded in that disk already, even though that star is forming. I'm going to show you a little cartoon. This is actually a numerical simulation. How do we think stars form? So this is a cartoon taking a spherical cow, hurdling to initial conditions, and in the eyes of the computer, evolving it for 40 million years. And what you're seeing is the collapse under the force of gravity of a small cloud. And we rotated, so you see the three-dimensional structure. It's filamentary, somewhat chaotic. And then we let the model continue. By the way, now 200,000 years has elapsed by the counter up there. And you see the first group of stars form. And notice that when you form one star, you tend to form many. Stars likely to form in groups. In fact, this little model generates something like 50 stars. And there's complicated dynamics. Mutual gravity of these stars causes ejections and accelerations. And there's accretion from the gas cloud onto these swirls, which are like the electromagnetism we talked about. But I refer to this as a cartoon, because it's missing essential physics. We assume that the gas is all the same temperature. It's not heated by the forming stars. We ignore the fact that observations tell us that young stars form jets and alphas. And we ignore the fact that it's magnetic fields. All of those things we understand to be important. And so more advanced models that try to incorporate those processes, but it's difficult to do so. So I'm going to show you a little bit about what reality looks like again. So this is a young low-mass star in Orion, called Early Carol Object 212. And we're looking at shock-heated molecules of hydrogen. There's a young star right in the middle. Two jets producing chains of shocks between them. About 2 degrees south of the Orion Nebula, there's this object called Early Carol 34 and 201 and 222. 201 is this object. 222 is this object. 34 is this jet. And this guy's like the Energizer Bunny. One shock here, a shock there, a shock there. Shock there, shock there, shock there, shock there, shock there. From one end to the other, we're talking about 9 light years. These jets can be in hundreds of miles per second over time scales of 100,000 years, impact parts of the cloud located many light years to the birth of the young star. Here's another object called HH47. Young star you cannot see. This is a visual wavelength image in hydrogen alpha, an ion of oxygen, ion of sulfur, wavelengths of 0.38, 0.65, and 0.67 microns, color-coded blue, green, and red. And I registered an infrared view. This is at 2 microns, 3.6, 4.5, 8 microns. You can see the central star drawn in the optical. There is the infrared. The jet is not really visible in the infrared, but a bubble is seen in shock-excited hydrogen. But by the way, notice all the background stars. Most of the stars here are visible easily. Red. But here, you only see the stars mostly in the infrared. Now, if we zoom in to that jet, there it is. It's a Hubble view taken way back in 1984. We came back 3 years later. See the movement? From the distance, we get the speed, 300 miles per second in space. By the way, this is looking in the northern part of Orion. I'm just going to point out this little complex called Early Carol Object number 24. You can zoom in on that. This is a ground-based view from Subaru telescope. There's one jet, there's another jet, there's a third jet, there's a fourth jet. There's a cluster of about 6 or 7 little stars forming right behind this little opaque cloud. If you go with the Hubble Space Telescope in near infrared, this is what one of those jets looks like. Little stars here, there's a jet, there's a continues like this, and it goes to the other side. There's a faint jet there. In fact, this thing looks like a lightsaber in Star Wars. That's a really highly collimated jet. All right, so for grading time, we're going to zoom into Orion itself, the Orion Nebula. And the tool we're going to use is this. The Gemini South 8-meter telescope, the Gemini South Adaptive Optics imagers, it's called, and 5 lasers. The 5 lasers paint in the stratosphere a constellation of 5 guide stars, artificial guide stars. We can lock an advanced adaptive optics system onto those artificial guide stars and make an image of a small field about 80 arc seconds in diameter that is diffraction limited with an 8-meter telescope. Achieve a resolution of 0.05 arc seconds, about the same as Hubble, from the ground at 2 microns wavelength. And here's what the Orion Nebula looks like. Here's the Trapezium stars. In the infrared, you see what looks like a 4th of July fireworks display. Now, this is not full resolution because the screen is low, so I'm going to zoom in and pan up from the bottom. So here comes the image. In blue, you see 1.6 micron iron vapor. Iron, which has been vaporized and lost one electron. In orange colors, you see shocks in molecular hydrogen. What the hell happened right in this region? So let's explore. In 1999, the Subaru telescope took this image. 2013, we went with our laser guides, our adaptive optics system, and took this image. Oops. And PowerPoint just crashed. So hang on. Okay. Yes, let's restart. Okay, it's coming back. Sorry about that. Glitch is happening. Quick review before the midterm. There's the horse head. There's a proton disc. There's the Karma array. There's the millimeter data feed we produced. There's the line again. Proton discs. All observations of the model. I'm not going to let it run. Almost back to where we were. A couple of jets. Now we're going to get to the real fireworks. Here we go. Back go up. Skip ahead. Okay. 1999, 2013.
Again.
You guys want to go back? Okay. You saw the movement, right?
Yes.
Okay. Ornery. Okay. We'll do a faster way of getting back to where we were. Okay. Here we go. I'm going to skip over that slide. It doesn't like something about it. I don't know what it is. But here's another part. Okay. Voila. The previous scene was the upper right. Now looking to the lower left. Here's 1999. See that object called source X? That's a star. Turns out that the distance between time interval 55 miles per second coming from about here. So we're going to go to the Atacama Large Millimeter Array. This is it. By the way, you think Colorado mountains are high? All the site is a valley, where the valley has an elevation of 15,500 feet. Why? Because to get access to these millimeter wavelengths, we do not want any water vapor. We want to be in the last place on the planet. The Atacama Desert is one of those. The higher you go on the mountain, the drier it gets. This is one of the best dry sites on the planet. There's perhaps two others. South Pole, Darn Pole, and there are places in Western China, which are competitive with the Alma site. Anyway, the mountains here go up to 18,000. It's a stunning environment for astronomy. We looked at the Orion region with Alma. Here's what we saw. This is a press release in 2017. Here's the magnesium, all the hundreds of low mass stars surrounding it. And then in carbon monoxide, we see what really looks like a 4th of July display. So here again is that adaptive optics image. And now registered to this is what Alma saw. And again, you notice that the colors again are doctor shift. The blue colors are minus 100 to 0. The red colors are plus 20 to 120. I cut out the rest velocity of the Orion clouds. It's too confusing. We just looked at the high velocity ejecta from this region. And what you've got is these streamers going on every which way from that location. And not only are there streamers, there are 3 stars. We already saw one of them, source X, moving that way 55 miles per second. There's 2 massive stars, the Vecna and Neugebauer object, which has a historical legacy because Eric Beckman, infrared astronomer, Jerry Neugebauer, Caltech. In 1960, used a military detector, a single pixel infrared cluster camera, 1 pixel camera, that was scanning. Looked at Orion, discovered an infrared star which had no visual counterpart. Published a paper being known as the Beckman Neugebauer object. First genuine infrared star ever measured, 1960. Today we know it's a runaway star moving to the northwest at about 30 times per second. The arrow is the amount of motion for the next 2,000 years. A little later we found another source called source I. It's visible only in the radio moving this way. All three stars came from where the gas comes from. There was an explosion there. Here's the summary of their properties. This is a 10 solar mass star. This guy is a 15 solar mass star. This guy's a 3 solar mass. These are massive guys. Trace back their motions to the X. Trace back the motion to the streamers to the X. Get an answer that something cataclysmic happened 550 years ago. From the masses of the stars and the motions, you get the kinetic energy. From the mass of gas and their speeds of gas, we get kinetic energy in the gas. You sum it all together. Kinetic energy of that explosion, more energy than the sun puts out in 10 million years. That energy came out in the course of a few years. Here, 175 AD. Signal traveled for 1,300 years to reach Earth in 1475 AD. And we're still studying that debris field today. By the way, I think this kind of explosion, not a supernova. Supernova is the death of the star. This is an explosion since the birth of the star. What happened? Well, in a nutshell, we think it was a stellar collision. See, these massive stars are all born in clusters, in a dense cloud. The star moves through a dense cloud, it experiences friction, drag, because of the gas. That means that the orbits of these stars, they move around a mutual gravitational well. Okay. The most massive stars lose their orbital speeds fastest. They all sink in the middle. They form a compact group. 3 stars, 4 stars, such groups are dynamically unstable. They will rearrange. One likely rearrangement is a collision coupled with ejection. I'll show you that in a minute. By the way, just recently, the Sophia telescope, which is a 747 aircraft with a 2.5-meter telescope sticking out the tail. That must take a look up the tail. Telescope looks out that way. And there's a polarimeter that measures the polarization. And so here's the Orion explosion, this magnesium, and the lines show the magnetic field. The formation of this region is caused the field to pinch, and then is dragged out by the explosion. Okay, I'm going to finish up here in a few minutes. We're going to really take you on a high-resolution tour of what happened 0.1 parsecs or 0.3 light years behind the Orion megawatt. You can't see it visually because this region is obscured by about 30 magnitudes. Even Hubble does not see the Beckman-Neugebauer object in visual or source X. Well, actually, that's not quite true. Source X is basically infrared Hubble, but not a visual wavelength. And source I can only be seen at radio wavelengths. I'll show you that in a minute. So here is actually a radio image. This is at the PLA in New Mexico, 48 gigahertz. There's source X, there's the N, there's I, and there's radio stars there. I'll show you in a minute. I'm turning off the arrows. Turn off. There we go. There's the N, there's source I, there's source N. Source X is not visible. How does this compare to a Hubble view? Next slide is hydrogen alpha with Hubble registered. There's one of these protoplanetary disks, or proplet, right there. That's an optical with Hubble. This is the radio. Whoops. Hubble, radio. Hubble, radio. You can see other objects like the star in the upper part of the image. You see the star in the middle, you see this shadow. Okay, let's keep going. This is now iron 1.644 laser dicer adaptive optics, same field, registry. This bright star is a Beckman Lodebar object, that runaway star. They retune their rise to 1.3 millimeters in the dust continuum, the so-called hot core. And by the way, you think carbon monoxide is a complicated molecule? In this cloud, astronomers have found thousands of spectral lines from heavy organics. Carbon is speaks like methyl cyanide, ethyl cyanide, ethanol, methanol. When ethanol was discovered, Lou Snyder quit. There's 10 to the 28 fifths of ethanol in the Orion hot core. If we could only tax it, we could fund all of astronomy. This is 11.7 micron, medium infrared. Again, that's a logo power option that depends on when SR dominates. Source size still not visible. So where's source I, you say? Is it really there? Here it is. Go to Alma. Here's DN. That's source I. By the way, this is a 0.05 arc-second resolution, so I have to zoom in. So here we go. Here's the previous view with the proper motions. I'm going to zoom this in a little bit. This is registered. This is source I. Zoom in. By the way, this is 1 arc-second. You have a good telescope, really good seeing. This is your resolution layer. Look at all it sees. It sees an edge on the disk around source I. And using the motions of molecules to declare rotation, measure the mass, that's how we figured out that's a 15 solar mass star. And now let's compare this to the VLA radio image registered. There's source I, the radio. You can't see the disk. You see another object down here called source N. It's really pretty bright right here. Okay. And there's an alpha. Here's how you measure the rotation. That's the Doppler shifts in color. Okay. Finally, I just want to show you a cartoon of what we think happened. We get this to run. Look like that was a spinning ball of death on the Mac. That's not a good sign. Let's okay. I have one more slide, which is my conclusions. So what we think properly. I'll tell you what the conclusions are. We think the last 100,000 years, a group of massive stars, along with about 2 dozen low-mass stars, formed in this part of the cloud. Over the 100,000 years, as these stars grew in mass, the most massive stars sank to the middle, forming what we call the non-hierarchical community, which interacted with gravity. 550 years ago, plus 100 years, 2 of those stars merged. They collided. Kinetic energy launched that star, a merger remnant, and 2 other stars on their way at high velocities, and also ejected about 10 solar masses of gas at speeds up to 400 miles per second. Some of that gas comes from the destruction of massive protoplanetary disks. In fact, some of the blobs that we see flying out, they actually protoplanets that were launched by that years ago. The message is that star formation can be a violent process. And in fact, there's evidence that our own solar system was born in such an environment. Why? Because if you look at primitive meteorites, we see radiochemical evidence that the primitive Earth, the material from which the Earth formed, was blasted by a supernova ejecta within a few million years of the formation of the first minerals we see in those primitive meteorites. We see the decay products of iron-60, neutron-rich species of iron which can only be formed in supernovae. We see in primitive meteorites decay products of aluminum-26, the radioactive species which again are produced by supernovae, but there's other ways as well. Those isotopes tell us that we were probably born from an Orion-like environment. The shenanigans we see in Orion today probably happened on Proto-Earth 4.5 million years ago. That's my story. I'll stop there.
We're running a little short on time. I want to take one question from an enthusiastic person. Right, Dr. Valley. And then he'll be available at the break and love to mix and mingle with you and come up and ask you questions during the break. Who's got one question?
So you consider the Orion as it is the formation of the galaxy started?
Not a galaxy, remember, galaxies started. Yeah. No, so the Orion is just a low mass, fairly nearby, typical fusion star formation. In fact, it's kind of limited because we look further into the galaxy, so that about 10 times the distance of Orion, there's a couple of fusions that we are studying, which are producing 100 times as many stars, and we're 100 times as energetic. If you look at nearby galaxies, like our closest galactic neighbor is a large measurement planet, can't see one. If you ever have a chance to go to Australia or South Africa or South America, look for the large measurement cloud. Even with a small telescope, you come to realize north is in the coverage. And all the best things in the sky are in the south. One eyepiece view with a 16-inch telescope on 30 rods going on the sea shows you a superstar cluster which has formed not 10,000 stars, but 400,000 stars in the last few years. And visually, a small telescope is spectacular, full of bubbles and structure. And right next to it, there's other things. And then you see F13 also here. When you see Omega Centauri, you can say F13 there. The point being, so my other interest is cosmology. When stars die, they make black holes. And one hypothesis actually goes back to T. Small, is that if you look at the Big Bang, imagine you see essentially collapse and everything. It essentially looks like a black hole. And so the argument that I just started in 1912 by T. Small is that massive black holes, supermassive black holes, are multi-tiny black centers. Essentially, our physics is taken to such extreme limits that when matter falls into the singularity, quantum mechanics reverses that approach and actually creates a space-time that's completely decoupled from ours. Not only that, the Small hypothesis says that the constants of nature are scrambled randomly. Each takes on some value. And the new universe comes out of this and have very different physics. In fact, change the mass ratio of the electron to the proton by 0.1%. Nuclear fusion and converts hydrogen to the heavy elements becomes impossible. Those universes will fail to make stars. If they fail to make black holes, that line of cosmic evolution dies. Those universes which may maximize the production of black holes reproduce. Now, as cosmology, the universe follows the laws of Darwinian evolutionist theory. By the way, this comes out of Billy's ideas about this so-called superstring theories. Or their ilk. There's other flavors of that theory. But there is what happens when you push physics to its extreme limits. How extreme? Length scale of 10 to the minus 33rd centimeters. If you do that, you will have a miniature Big Bang on that. That's a whole other subject. That's another one. Thank you.
John, thank you. I wish I was 30 years younger. I would join you at Steve Boulder and take your class. That was inspiring. I really enjoyed it.
Are you still coming to attend class?
I'll come and audit.
Never too late.
We'd like to present you with the very most collectible sought after thing that this club has to produce. It's our coveted mug. Take it with our thanks, and we really appreciate your coming.
Thank you.
So what I'm going to do is I'm going to move observing reports, and we have Fred. Fred is going to talk about our telescope inventory. We'll move that after the break. And can we make that a short break and come back at 7:55? And please take the opportunity to ask Dr. Valley questions during the break. This is a short break because we are running.
Peak and the road going up to Pikes Peak, and it was kind of cool. The next one is another moonshot. And this one is,
Sorry, stand by.
yeah, okay.
We got a draft.
Just,
There's the amount.
there it is, yeah.
Okay.
And this was a full moon. I think this was the March full moon. You know, we had four, I think 3 or 4 full blood moons this year. This was the March full moon, 1/200 seconds, ISO 200 and F11, 300 millimeters again. But I really like this one because you can easily see the man in the moon and the Tico crater there. It's really, really cool to see. He's going to get going into astrophotography just to photograph the moon. The next one, Garden of the Gods. Again, daylight, and of course there's the sun, which is a star, and I thought that was kind of a cool shot. The sunburst over one of the rock structures at Garden of the Gods. And that was also 1/200 second ISO 100 and F11 for using 18 millimeter lens. Okay, the next two I just did a couple weeks ago, which I really wanted to get into. This is the Milky Way over 11-mile reservoir, and this was using a Nikon camera. 13-second exposure, 3200 ISO. And this is actually the city lights of Denver bouncing off the clouds. You can see it here in the water here. Milky Way, this is the Galactic Center right here. And so this was the very first time I ever going to try photographing the Milky Way. It tended to do better, but it was a good first attempt. And the last picture that I have here, this is another shot of the Milky Way, which was taken about 2 a.m. It might be hard to see because it's darker, but you can definitely see the Galactic Center better. It's thicker, deeper star cluster there. And that one was ISO 2500, 10-second shot. So anyway, is Barry here tonight? I don't think he's here tonight.
Over here.
Okay, well anyway, thanks. You gave us some really good tips.
Thumbs up.
This is your handout. That's what I followed.
Oh, good.
So if you want to get into this, talk to him and go to his novice class. Thanks a lot, Barry.
Thank you.
Actually, I don't have any pictures, but I just wanted to make a quick a report, if you will. July 2nd, there was a total eclipse of the sun, but you had to be in Argentina or Chile to see it. So I made arrangements to be down there to see it, and I made it with 30 minutes to spare. Wow. That's a whole other story. I got some pictures, but they didn't turn out as well as I would like.
This is favorite error.
It's not both. It was, I mean, a total eclipse is what do they call it? The nature's greatest spectacle. It really is. It was another great eclipse to see. Actually, it had a double diamond ring in the star, which I've never seen before. Then 4 or 5 days later, the group that I put together, we found ourselves in Chile in the Acre Valley, which is where Cerro Tolobo, I'm not sure if I'm pronouncing that correctly. That's where a lot of the big giant world-class, multi-meter telescopes are. They also have about a dozen or more astro-tourism observatories, private observatories that you can reserve and go to. We went to one. We were at about 3,000 or 4,000 foot in elevation. We had 2 hours on a me 16-inch telescope to look at the southern Milky Way. And that was incredible. As Dr. Dr. Bailey was saying, if you ever get an opportunity to go to the Southern Hemisphere and look at some of the highlights, they'll blow you away. And I'd seen it before through my small 80 millimeter, but a 16-inch really, we could see the homunculus nebula in Eta Carina. It wasn't quite as nice as the Hubble telescope picture of the clouds around the Eta Carina star, but you could see it really. Things like that to see with your naked eye through a telescope is really special. So I just wanted to give you a report on that.
And how many total eclipses is this for?
5.
How long was this?
What's that?
How long was it?
The duration, if we could have made it to center line, it was 2.5 minutes. We got about 2 minutes of totality. we had to pull over the side of the road to stop at that point. We had missed we were 24 hours, we missed our flight from Houston to Buenos Aires, and we couldn't leave until 24 hours later. It's like, oh, I wasn't sure we could even make it at that point, but we did.
Gotta move on.
Okay.
Thanks, Tom. Next is what's up, and a quick one. Will Keebaugh, are you here? You signed up for a badge, and Vicky cross-referenced you being here, so there's your badge.
We're sharing, now we're sharing that. Okay.
Okay, what's up?
Since you want to use the, I think it works. If it doesn't work, I'll just advance for you.
Okay, so the what's up presentation, these are things that are a little bit easier to see, and then I always like to highlight a couple of the objects and give the backstory, which makes it interesting, to me at least.
No?
Next slide.
Okay, hang on. Let me get to. I think I have to get the cursor in here. Just click.
There we go. Okay, thanks, Scott. So always start with the winter information if you're interested in that. Of course, we generally don't like to, and so I started saying, well, maybe we should name the new moons instead of the full moon. So we've got the full and the suggested new moons. There was a new moon earlier in July, and I think obviously that was the RMSS new moon for all that spectacular viewing that we did. And then there's a full moon just about a week ago, mid-July, and that was the Bucker moon. They used all that for the route. And then late July, there's another new moon at the end of the month, which is fortunately placed for a couple of minor meteor showers that I'll get into. And I would suggest maybe we call it the Milky Way new moon, since this is perfect location for the Milky Way to be rising. And then in August, the full moon's 15th of August, and it's the Sturgeon moon. And then one more new moon in August, but we'll meet before that, and maybe we can call it the Swan new moon, the Cygnus the Swan will be up high. Next slide.
Okay, go ahead and try your clicker, see if it'll work now.
Yes,
there you go.
All right. Technology. So in the next couple of slides, what I was going to do is show the constellations that are rising at twilight, looking east on the new moon in about 2 weeks, give an idea of what's coming into view there, and then looking at midnight towards the south and towards zenith. So towards the rising here, we can see a lot of our summer constellations get well placed up. Cygnus the Swan and Cepheus the Kingdom looks like a house to me, and Altair the Eagle and the Summer Triangle, of course, these three here, Vega, Deneb, and Altair. And so we're definitely in the summer season for good viewing, and there are a lot of objects, as you will see there. But ones that I would like to highlight. So if you're looking south towards midnight, new moon, we've got actually this beautiful lagoon nebula that Bob showed a photograph of. And good placement for viewing, about as high as it's going to get. Saturn, of course, being close to opposition, but also its highest point in the year. And then Jupiter a little bit past prime, but still in great placement for looking at, and still quite bright because it was closely near opposition. Looking straight up, then of course that summer triangle has now moved up towards midnight, and we have a lot of the sky within reach for us. So a couple of other things that we can see there that are really easy if you're starting out. Look at this M57 or Messier 57. Charles Messier was a comet hunter who kept getting fooled by non-comets, so he made this list of things to not get fooled by, and they turn out to be really good ones to actually jump in and look at if you've got a new scope or you're trying to find something. Ring Nebula is one that's easy to find. It looks like a smoke ring, and it's in this constellation Lyra. It's hard to see, I know, but this looks like a parallelogram, and you can go to the shorter edge of the parallelogram, go right in the middle, and you're going to find this thing. It's a planetary nebula. I'll get into some information. Dumbbell Nebula is kind of the same thing. So stepping back, that Lagoon Nebula, Bob had that great picture of. This, of course, is a picture from NASA looking at a much more close-in view, and dark nebula regions and dust, and this lost a lot of its punch after Professor Valley's presentation with all the awesome stuff. So, but what is cool about these is, so this one's a reflection nebula, and again, he mentioned that these are shining not of their own accord, but new stars that are being born. So we can actually see the dust cloud that are causing the formation of new stars, being illuminated by those new stars, kind of like a fluorescent light bulb lights up with the gas that's surrounding this intense magnetic field that's in there, an electric field that's in there. That dumbbell nebula that I talked about looked gorgeous from Rocky Mountain Star Stare. It's fairly simple to find if you look at Cygnus and Swan. And on the south side, if you try to make the Swan, it's kind of, it looks like the Northern Cross, as folks call it. If you made the lower quadrant a rectangle, where there's a missing star that would make the rectangle, turns out to be this object right here. This is a little bit different. This one is glowing because it's a planetary nebula, and there's a dying star or carbon star forming at the center of this thing that's collapsing down and lighting up its own atmosphere that it kind of blew away as it reached the end of its life. So these stars go kind of through these life periods. They burn hydrogen into helium and then helium into carbon eventually. And so what happens there is if the star's not big enough, it ends. And there's quantum mechanic reasons for that to be the case. But the thing that is really fascinating is time span. It takes like 8 billion years for our sun to burn hydrogen and helium, and then a few 100 million years for the helium to burn up, and then the carbon exhausts its fuel source, within like hundreds of years. It's sometimes shorter than that, a ferocious amount of energy, and it loses a lot of its atmosphere because of all of that heat, basically, that it's putting off, among other complicated things. This was a different spectrum of it, the infrared spectrum that the professor showed some of these. This is M27 in the infrared. So a different view and quite a few cool things that we can see. This is kind of something that I found on the web, Luther College put from their observatory. This is kind of what we could see in our telescope, say a good 10-inch scope from like Rocky Mountain Star Stare, Starry Meadows, could see something that looks a lot like that. And then that ring nebula, you won't see the colors there because your eyes don't integrate and see colors in the dark, but you will see a smoke ring that looks a lot like this, and that's a really nice object as well. From suburban skies, you can see this. Usually it's better to get help of a special filter called an O3 filter. If you come to one of the star parties, if somebody will bring one you can borrow. See this from the star party through your telescope. Really nice object. The filter actually throws away all light except for light caused by certain molecules the professor talked about, carbon monoxide, this one being oxygen, decaying in a certain excited state that normally wouldn't decay. These atoms would not decay this way on Earth because they would find another atom to bump into and lose energy to decay through just kinetic collisions. But in space they can't, so they emit a photon instead. That's so rare, it's called forbidden radiation, so that's kind of cool too. Helps us see things, increases the signal-to-noise ratio by throwing away all the other light sources that would normally be signals. So planetary nebulas and reflection nebulas. But then lots of Messier objects, and I'll get into that. Comets, we're still kind of in a drought for comets. None are better than 10th magnitude right now. There are a few that are expected to. There's one discovered back in 2018 that's expected to be greater than 10th magnitude in September. Another one that the Pan-STARRS automated telescope found that should brighten up, maybe quite bright according to the alpha folks who reported on it. There are 3 meteor showers. These southern Delta Aquariids, the zenith hourly rate about 16. They're moving fairly fast, and their peak is right around the new moon, so that's kind of fortunate. Same thing with these alpha Capricornids, about 5 of those an hour. They're relatively slow, but again, their peak is right around the new moon. And then the Perseids, which is one of the best shows of the year, but unfortunately falls right around full moon. You can still see some of those. It's fairly broad peak, but it's very sharp for the fastest one. So anyway, it's unfortunate, but that shot, new moon evening, you should be able to see a few of these meteors as well as sporadics.
What's the date for the Perseids?
Perseids are, the 12th of August would be its peak, but with the full moon, it's really going to be suffering. So then Jupiter and Saturn, of course, being the best planets to go after. Mars and Venus are pretty much lost in the solar glare at this point. Neptune's not so bad most of the night, actually. If you're going after the fainter ones, those are harder to see. And then Uranus, same way. Mercury, depending on what time of the month it is, you can see it racing just before the sunrise. This is where those meteor showers are going to be. And so if you know these constellations at all, of course, this being Pegasus and Aquarius, and you're looking down kind of towards the south, let's see, that would be southeast, about, I put this in, just past midnight on the 31st here. That's where the radiant for these meteor showers are. Now, you don't necessarily want to stare where the radiant is. Meteors could be anywhere, but they should be, if they're correlated to one of these storms, look like they're coming back to that circle if you were to connect the line that it came from. And the Perseus, of course, over near Perseus and Cassiopeia, kind of more towards the northeast, but not going to be so great because of the moonlight. So the easier targets that I would go after, again, I highlighted some of these. We don't have time to get into all of these. I'd go after probably the Ring Nebula because it's nice and high right now if I was going to go after something. This gives you an idea of all the good stuff that's up there right now. If you're interested, I can give you a copy of these slides. Track down a lot of these for RMSS. So we benefited from my preparation for RMSS. And this was one slide that I had from a different presentation, but just to show the signal and noise idea. This is kind of like Sagittarius normal. This might be the way we would see it from a suburban sky. And it's pretty simple to see the old teapot handle and the spout. And, you know, that nebula that Bob talked about, I always think of this, it's up here in the steam cloud, and it's fairly simple to point to. And then you get to like RMSS, and there's so many stars that you just start to lose things there. So anyway, that's what's up.
Okay, so we've got about half an hour's worth of committee reports to do in going to end the meeting on time. This is time for our committee reports, and Tom DeClue would like to give us a brief report on RMSS.
Sure. How many people here went to RMSS? So I got to tell you that this was my 22nd one. I don't remember an RMSS where the weather was so warm. It was perfect weather every night. Although I had to leave Saturday night to get the plane the next day, but
It was good then.
But I heard it cleared up and Saturday night was really good too. So we got spectacular weather, combine that with the best turnout we've ever had. We had, I think, 352 registered, although not that many actually was on site. We always have some percentage that can't make it for one reason or another. We had again, great speakers. The facilities were in really good shape thanks to Henry Barry Young over here and his team that did so much work to get the site ready. One other thing I wanted to mention, these are the packets. So is there anyone here that registered for RMSS but couldn't make it for some reason or another? Anybody? Okay. Well, in that case, but these are the people that didn't pick up packets. So if you had a packet you didn't pick up, you're going to be for it's worth. So this year's RMSS is in the can, so to speak. We will be. I would tell you, September is usually historically when we have our first planning meeting for the next RMSS. That's going to be RMSS 2020. We don't yet have a director. I will be the deputy and the assistant director when that event for next year. So we still do need a director. So that's something to think about. Okay, guys?
Think about it and take it deep into your heart and seriously consider it. Tom, you'll be there to help out.
Oh yeah, no, I'll be the assistant.
Okay.
You bet. Thank you.
All right, thanks. And can we follow that up with our treasurer's report and how RMSS affected our coffers?
Yeah. Oh, I'm sorry. How did that get up there?
I'm sorry.
Geez, let me pull that back. Darn, I'm still getting used to running.
That was the slide I made about the big interview.
Okay, first of all, Matt Russell wants to thank everyone for birthday wishes and monitoring as we go along. Treasurer's report, very briefly and succinctly. First of all, if anyone has any detailed questions, see me after the meeting. I'll be happy to do that if you remember. Bottom line is on the CSASTRO account for the club itself. We're basically up about $1,130 for the year. So that's revenues over expenses. So good there. On track budget-wise.
for the Starry Meadows RMSS. We're basically about $3,600 ahead from where we started at the beginning of the year. And considering that we had about $12,000 in capital expenses for finishing the electricity to the building at Starry Meadows, plus finishing the observatory, essentially our proceeds from RMSS pay for itself, plus pay for those two capital expenses. So, great news.
Special interest group.
Real quick, just three things. One is our normal applicant meeting, which is held 1 week from tonight at my home. If you don't know where that is, or if you haven't received any contact from me, please give me your email address so I can read it, and then I'll give that information to you. Next week, we're going to concentrate on yeah, thank you. Stacking, and we'll try to go through not just the capturing of it, but also a little bit of the processing of it. 2 days following the meeting at Berry's home, where we'll have the novice groups, and that we're trying to go through a kind of a walkthrough of the setup and then imaging. If there is no interest in it, and I haven't received anything back yet, but I'll kind of notice. We may extend that to a part B of that night, which would go from like 8:30 to like 10 or so. We might go to a location and actually allow you to use your equipment to try to capture something. And then finally, so we can help you actually do that. So that should be good. The last piece of information is I have sent out for all those that are part of the agency group a kind of a survey of topics we'd like to cover for this year. And I'm trying to base it on what the greatest needs are. I have received about 7 or 8 back. If you still would like some input on that, on something that you have a need for or really want to find out more about, you know, contact me, and if you haven't received it already, I'll get that for you. And then your input will help determine the things that are valuable that we covered. So take me afterwards if you need to contact. Thank you.
Brian and Bruce, long-term planning, and you had something about Dark Sky Initiative.
Yes.
Or file a copy?
Huh?
Dark Sky Initiative.
Dark Sky Initiative. Most folks know that one of our dark sky sites that's relatively close to here is the Florissant fossil beds. Can everyone hear me? You don't need a microphone to see. Never. Just want to let you know we're making some good progress. I'm going to pass around. We just had a recent survey done of the site. So this is an opportunity so you can actually see how dark those skies are out there. And it looks like this is going to be a cinch for them to be qualified as a dark sky park. That team and committee will let you know as we're submitting and so forth. But this work has been going on for the last year. We're getting close to the final data collection. We're going to be there for all that bit. Second item. Long-term planning committee is currently invested a lot of time and effort into finding a home for the Air Force Academy telescope. We are now setting up appointments with several folks who are interested in providing that a home. At this point in time, I'm not at liberty to discuss the specifics on that. If you want that, attend one of our committee meetings. That's the easiest way to do it. But realize, for those people who don't know, we inherited a 24-inch historical Bolsheviks, a telescope that actually did some of the initial surveys for the Apollo landing sites in its earlier days, and has been up at the Air Force Academy for years. It is ours. We need to find it a home. So that's where our effort is going to work for that. Third item, this is just as my role as a trustee. Elections are upon us soon. If you are considering running for an office, and I highly encourage you to do that, please find someone who's doing that office right now and go talk to them about the office that they're doing. Some of our folks may want to run again, but that doesn't mean we can't have competition. And please, the healthiest club has a turnover of the officer and board members because that keeps everything fresh and lets everyone know that it's not just the same old bunch of boring people up here putting you to sleep. So please consider that. We take nominations next month, correct?
Correct.
All right. Questions? Thank you.
Hey,
Bruce.
Bruce.
Bruce, Barry Young, or also known as Bear.
How many seconds do I have?
3.
Tim, you can have 1 minutes.
Okay.
Talk about Star Meadows.
The land committee just did a knockout job. And I mean, I say that for on behalf of them. They did a lot of work. Their hard work resulted in being on time for Star Meadows. We didn't have any projects we couldn't complete. Came in almost $900 under budget. $500 of that was because 4 guys got out there and backfilled the trench with me with my snowplow blade, and we tamped it all down and got everything going. And I'm surprised it didn't kill me when it was all over. But it was very nice of them to put forth that kind of effort. We've got enough extra money left to go ahead and make some other improvements that we want to make Star Meadows. Now, tomorrow I'm going to be posting some documents. I'll post a link to documents out on the forum. And if you're interested to see what we did last year, and in the last, I look at it, like 2018, 2019, now we're 2019, 2020. We're even looking at 2020, 2021. We're looking out that far. You can look at the documents and see the things we're discussing. And we always ask you, if you've got a comment, you can email me. And I will have my email address out there. Feel free. I like your comments. Even if you can't make the meetings, we don't care if you can't make the meetings. We'd like to get input from you. And I think that worked out really well this last year. We have more time. We will thank the individuals that helped. There was a lot of people that really engaged. We've got some folks that gave 4 or 5 days in a row, came down 2 or 3 different times. And I do want to thank the club for the really nice observing chair. That was a wonderful gift that they gave me at Armin's Nest, and I so appreciate that. Really set that on behalf of the team, because we've got a very good team. And not only that, the nicest part of just in closing, I want to say, the nicest part of this committee to me has not been what we accomplished, but it's seeing the members get together and accomplish a common goal. But I've seen more friendships form and a lot of bonds. And I just thought, man, that's what it's all about. It's not just about build a building or anything like that. It's the friendships that have been made. And it's touched me pretty deeply. So thank you very much.
A round of applause for all the volunteers that helped Barry out. Barry's just done a superb job down there at Starry Meadows. After the meeting, he's got a poster that he'd like to share with people, just to hang in your bedroom.
Well, I'd like to, take a look at it. It's right over there, and I'll set it up over here. But I got it in like 1965. I would have been 8 years old, and it's pre-Gemini, pre-Apollo. They actually show a Gemini coming in for a land landing, and I mean the view of the Apollo capsule looks like a room at the Holiday Inn. So take a look at it. Kind of fun to see it.
All right, Dave Warner, outreach.
All right, first of all,
minus 1 minute, but I think we'll be a little flexible.
We'll go fast. First of all, Barry, just like you guys have with the land committee, outreach is the same thing. We get together under the stars with our telescopes, and we have that same sort of bonding in getting to know not only how our telescopes work in the night skies, but get to know each other. And it's a great team that we have. We have some outreach coming up that if you're interested in learning how to use your telescope and can help with showing people the stars, come on out to one of our events and participate. Even if you can only point at Jupiter or Saturn, that's okay, because lots of people like to see Jupiter or Saturn. If you don't even know how to do that, come on out, set up your telescope, we'll help you get pointed, look at what somebody else is pointing at, copy them, come over, then you can start doing the same thing and getting involved in the outreach. To date, we're at 60 events completed. We're just shy of 10,000 people reached for the year. The year's not over yet. So what we have coming up is on Friday, we have fluorescent fossil beds. As you saw, a great dark sky location. It's a great place to come out with your telescopes. We set up in the overflow parking lot area near the visitor center. We come out there and just set up our telescopes. We'll have 7,500 people out there coming to look at the stars and the planets that we have to see in those dark skies. Great place to come and just enjoy getting out of the hot weather in Colorado Springs and getting up there in the mountains. It does get kind of cool up there, so bring your jackets and be prepared for that cooler weather. But come on out, it's a lot of fun. Then also on the 27th, on Saturday, we're going to be at 11 Mile State Park. We're going to be in the little parking lot playground area that's immediately adjacent to the North Marina. When it gets dark, it's a little hard to find, so if you can't figure out where that is, look on our calendar. In the calendar event, when you click on it, I did a Google link, not the Google map that's there, but the link itself. You can go and see exactly where we're going to be setting up. But we're expecting about 150 people potentially from the state park coming over and wanting to look at our stars. You saw a picture of what it looks like at 11 Mile, dark skies up there too. So we're going to have a lot of fun this weekend in a couple of dark sky places. Not on the calendar, and I still have to post it, just got the final details worked out on Tuesday. We're going to be up at the Catamount Institute. They have a camp up there for about 40 kids. We're going to come up there with telescopes and show the kids at a camp the stars. Catamount Institute is just north of Woodland Park off of Edelwood Road near Catamount Reservoir, so why it has this name. But then on Wednesday, we have our Space Foundation Discovery Center start party. We set up our telescopes right outside of the Discovery Center where you're at right now, out in the parking lot. So that's also a really good time to bring your telescopes out. If you're a new telescope owner, want to get to some familiarity with using your telescopes, that's a great time to do that. We'll have the lights out in the parking lot. We do have to compete with the trees a little bit, but again, we'll have Saturn and Jupiter, and we could be working on some of those objects that Vince said, here's the objects that you can get started on and get to see. Those are the things that a lot of times we're looking at when we're doing outreach. So it's a good way to get started in learning the night skies. As we get into August, on the 3rd of August, we'll have our public star party. It again is at Palmer Park. We're still working those issues with the El Paso County Parks and Recreation, who close their parks at 9 o'clock. Palmer Park stays open till 10, so we have that park to use until such time as we can get those issues resolved with the Parks and Recreation. Hopefully we'll do that sometime in the future. Now when we go into August, when we get to the 7th of August, that's a Wednesday. I'm sorry, not this. Yeah, I'm sure it's the 7th of August. 7th of August, same thing. We're going to be at Garden of the Gods for a star party. We set up at the visitor center in the RV bus parking lot. And last one we had in July, we had 350 people, 450 people there. So lots of people. The more astronomers we have out there with telescopes, the better off we are. So that's pretty much what we've got for up until our next meeting in August. I think there might be something else. Actually, Mueller State Park called me this morning and wants us to come out again in August. So we'll be setting up a Mueller State Park event in August. So there's also a KRCC member star party. We'll just have a couple of people doing that event. That's downtown in a park next to KRCC, where we'll set up our telescopes, and the members get invited to that star party so we can go show them that. Mike Purcell is on KRCC. He's leading that effort up and having us come out and do that. If you're not familiar as well, I should mention that on Mondays We have our Colorado Springs Astronomical Society members that do their podcasts and their talks on the radio on KRCC radio. And you want to talk about that real quick, Bruce? And that's all that I'll have for this month for outreach.
This is Looking Up in Southern Colorado at krcc.org on Monday nights at 9 a.m. and 9 p.m. Al Penlack and myself do the two voices for that. We occasionally have other guests coming in. So, here's
the bases of radio.
I got a perfect face for radio.
Yes, I'm sorry, there's one more outreach event, August 1st and 2nd in Rocky Mountain National Park at the west entrance, Holsworth site. We'll have outreach. Circuit, we've done it. We have over 2 nights, we have about 300 people.
Okay. If you're supporting that and you're a club member, but after it's over, you want to let me know how many members supported, how many people you reached, and dates and times, I can get that recorded in the Night Sky Network so that we can get credit for that. And also that gets us grant monies when they're putting in for grants and also free stuff that NASA sends us based on our activity as a club. So thank you everybody for all your support and doing outreach. I look forward to breaking 10,000 over this weekend.
Hey, Doug. Bill, I noticed for the next meeting, we have the summer picnic. That's coming up, right? So we probably ought to let people know about that.
Okay, that would have been George.
We're going to have a summer picnic. Look at the calendar.
Look at the calendar. And are we going to send out an email reminder? And
We'll need to do that.
yeah, we'll send out an email reminder for the summer picnic. About this room, I know this was the first time we've been in here. Our drill in the other room was to put everything back in a classroom configuration. We don't have to do that tonight. But please police the area, socialize a little bit, but let's be out of here by about 5 minutes to 9. We'll give us about 15 minutes to be out of here.
Right there. 24th.
And then it should be a Black Forest.
Good job. And that's tough. We've got to figure out how we're going to run that stuff remotely. I guess the trick is you move your mouse over there and then you can use the keyboard. You can go full screen or whatever.
There are dues to, is it 12 months for the person or is it annually based on?
There's annually, so there's two options. Annually, depending on whatever month you started up on. We also have for one-time $300 lifetime.
Are we going to go ahead and apply?
Go to the calendar. We can apply for tax credit in my house. I just went to the post office today. I sat down.
Email goes down and give it to
So you
Brian.
get it, I sat down
Where Brian is?
So
I'll get you. I'll get him for you. He manages the email list. Or you can yours. All right. Here, I'll write it in for you. Let's do that. I'll just write it down for you.
Oh, I need to stop the recording here.
Delete mine off of there.
Yeah, I need to stop recording first. All right.